Welcome to another deep dive. Today we're going deep beneath the ocean floor to explore the fascinating world of deep sea drilling.
Fascinating is right.
Yeah, we'll be uncovering secrets of our planet's past and present, and maybe even a glimpse into the future.
It's amazing what we can learn from the rocks and sediment buried miles beneath the waves.
Seriously. Our source material takes us on a journey to the Japan Trench,
Oh, wow.
one of those geologically active places on Earth.
Yeah.
And get this, we're joining a team of scientists aboard a drilling vessel
Oh!
called Chikyu. It's a state-of-the-art research vessel.
The Japan Trench is a pretty intense place to be doing research, especially after the devastating 2011 Tohoku earthquake and tsunami.
Right, it was a stark reminder of just how powerful nature can be.
It really was. And that event sparked a global effort to understand what causes these massive events, and that's where Chikyu comes in.
That's right. This vessel is designed to drill up to 1 kilometer beneath the seafloor, in water that's about 7 kilometers deep. To put that in perspective, imagine drilling through Mount Everest, but underwater.
That's incredible.
It is. And they're using some seriously advanced tech to get it done. Risers, which are these giant pipes that connect the drilling rig to the vessel itself.
Oh, okay.
They've got specialized drilling rigs that can withstand the immense pressure down there, and core sampling systems that bring up pieces of Earth's history.
Like an underwater time machine.
Exactly. And it's not just heavy machinery. They're also using ROVs, underwater robots. They help inspect the drilling site and even deploy scientific instruments.
I mean, that sounds like something straight out of a sci-fi movie.
Right. It really is amazing how far technology has come in helping us understand our planet better.
I agree.
But what exactly are they hoping to find down there in those depths?
Well, those core samples are like time capsules from the Earth's past. Scientists believe they hold the key to understanding and maybe even predicting future earthquakes and tsunamis.
Okay, but how can a piece of rock help predict an earthquake?
Well, think of it like this. Rocks are like records of the forces they've experienced. By analyzing the rock formations, their density, the spaces within them, what we call porosity, and even the fluids trapped inside, scientists can understand how those rocks behave under stress.
Interesting.
It's kind of like a detective examining fingerprints at a crime scene. They're looking for clues that reveal the history of seismic activity and potential triggers for future events.
So imagine being able to predict earthquakes with more accuracy, giving people time to prepare to evacuate, potentially saving countless lives.
That's the ultimate goal, but getting those core samples is no walk in the park.
I can imagine. We're talking about extreme conditions.
Immense pressure, freezing temperatures, corrosive salt water. It's like working in a pressure cooker inside a freezer at the bottom of the ocean.
Whoa, that sounds incredibly challenging.
Oh, it is. But these scientists and engineers have developed some seriously impressive techniques to overcome these obstacles. Advanced drilling vessels, incredibly robust equipment, real-time monitoring to make sure everything's running smoothly, and of course those ROVs we talked about.
So it takes meticulous planning, international collaboration.
Yeah.
It's a huge effort.
It really is a testament to human ingenuity and our desire to understand our planet. And this is just the beginning. We've only scratched the surface of what we can learn from deep sea drilling.
Hold on, everyone, because it's about to get even deeper.
So we're back going even deeper into this deep dive into deep sea drilling.
You deep dive into deep sea drilling.
Oh,
I like that. But really, though, why the Japan Trench? It's not exactly vacation destination.
All right. Well, you've got to remember that 2011 Tohoku earthquake and tsunami, the one we talked about earlier, it was a huge wake-up call for scientists.
Yeah, definitely a tragic event for sure.
It really showed us just how much we still don't know about these massive mega earthquakes. And the Japan Trench, where that earthquake happened, became a prime location for research.
So it's like a giant natural laboratory for earthquake research.
It's what's called a subduction zone, which is where one of Earth's tectonic plates is being forced under another. It's a slow-motion collision, really.
Okay.
And it's this kind of tectonic tango, you could say, that causes those incredibly powerful earthquakes and tsunamis.
Okay, so we've got these massive plates, these giant puzzle pieces moving around and sometimes crashing into each other.
Yeah.
But why focus on Japan specifically? I mean, couldn't they study these subduction zones in other parts of the world?
Well, Japan has a long history of earthquake research. They've got the infrastructure to support these complex drilling operations, specialized vessels, a whole network of scientists dedicated to this.
So they're kind of leading the charge when it comes to earthquake research.
In many ways, yes. And another crucial element is the international collaboration. The Japan Trench Fast Drilling Project, or JFS, brought together scientists from all over the world.
A global team effort.
Right. They pooled their resources and expertise to achieve this ambitious goal of drilling right into that fault zone.
Wow. So a global team effort focusing on this one specific location.
Exactly. And by studying the Japan Trench in such detail, scientists hope to gain insights that can be applied to other subduction zones around the world.
Okay.
It's all about understanding those underlying mechanisms, that trigger earthquakes so we can better prepare for them.
So it's like they're trying to crack the code of earthquakes one trench at a time.
That's a great analogy. And one of the fascinating things they're doing is trying to look back in time.
Wait, how do you look back in time through earthquakes?
Well, it's all about meticulous analysis, a deep understanding of these geological processes. Scientists look for clues in the Earth's layers, kind of like a detective piecing together a puzzle.
So what kind of clues are they looking for?
One thing they look at is earthquake recurrence intervals. By analyzing past earthquakes, they can identify patterns in how often these events occur, like trying to predict when the next big storm will hit, but on a much grander scale.
So it's about finding those patterns in the chaos, trying to figure out if there's any predictability to these earthquakes.
Exactly. And it's not just about timing.
Right.
They also look at how these faults, those breaks in the Earth's crust, have behaved over time. They look at how fast they're moving, how long the ruptures are, how much stress builds up before they release all that energy in an earthquake.
It's almost like you're trying to understand the personality of a fault line.
That's a great way to put it. So it's about understanding both the timing and the behavior of these faults.
Okay.
And don't forget about tsunami potential. By looking at historical records of tsunamis, scientists can assess how likely future events are and help design those crucial early warning systems we talked about.
So they're really trying to piece together this whole history of seismic activity, from the earthquakes to the tsunamis.
Exactly. And by focusing on a single plate, like the Pacific Plate in this case, they can really delve into the details.
But how does focusing on just one plate help us understand the bigger picture of plate tectonics? It's like looking at one piece of a giant puzzle, right?
That's right. And while you need all the pieces to see the whole picture, studying a single piece in detail lets you really understand its shape, its colors, its unique characteristics.
So it's about getting both the granular details and the broader perspective.
Absolutely. By focusing on a single plate, scientists can study its movements, the stresses that build up, and how it releases that energy. This helps them create more accurate models for predicting what might happen in the future.
So it's both specific and broad in its approach.
Right. But we can't forget that plates don't exist in isolation. They're constantly bumping into each other, grinding past each other. It's a very dynamic system. So scientists also consider the bigger context of plate tectonics.
Like how the Pacific Plate interacts with the North American Plate at the Japan Trench.
Exactly. The movement of one plate can affect the others, potentially triggering earthquakes in seemingly unrelated regions. It's a complex web of interconnected forces.
It really makes you appreciate just how dynamic and interconnected our planet is. But with so many plates out there, why not just study them all in equal depth?
Well, that's a good question. But practically speaking, it comes down to priorities and resources. Regions with a history of strong earthquakes and a lot of people living there, like the Pacific Ring of Fire, naturally take precedence.
Those are the areas most at risk.
Exactly. And scientific research, takes a lot of funding, a lot of resources. Focusing on key areas allows for more in-depth study and a better use of those resources. Plus, scientists can build on existing knowledge, constantly refining our understanding of those specific areas.
So it's about making the biggest impact, get the resources available.
Precisely. But while focusing on certain plates is important, understanding their connections is crucial for that complete picture. By studying multiple plate boundaries, scientists can get a much more comprehensive view of Earth's dynamic processes and improve our ability to predict and prepare for natural disasters.
It's a balancing act between focused research and taking that wider lens.
Exactly. Now let's dive a bit deeper into soil analysis and how it helps us understand the timeline of seismic activity. We touched upon paleoseismology earlier, but let's really dig into it.
Let's do it. I'm fascinated by the idea that the ground beneath our feet holds clues to the past.
Think of the ground like layers of a cake.
Okay.
Each layer represents a different period in time, and within those layers we find evidence of past earthquakes. It's like reading a history book written in the earth itself.
Okay, picturing those layers. So what kind of evidence are we talking about?
Geologists look for signs of disruption, like features caused by liquefaction fault scarps, which are like steps in the ground caused by movement along a fault, or changes in how quickly sediments were deposited. It's all about reading the subtle signs left behind by past earthquakes.
And how do they know when those earthquakes happened? It's not like they have dates stamped on those layers.
That's where radiocarbon dating comes in.
Okay.
It acts like the page numbers in our Earth history book telling us when those events occurred. It's a technique that analyzes the decay of radioactive carbon isotopes in organic material, helping scientists pinpoint the age of those layers.
So they're combining those visual clues with scientific dating techniques to create a timeline of past earthquakes.
Exactly. And soil liquefaction is one particularly fascinating phenomenon they look for. During strong earthquakes, the ground can literally lose its strength and behave like a liquid.
You mean like quicksand?
Yes, exactly. It's a dramatic example of how earthquakes can transform the very ground we stand on. By analyzing soil samples, geologists can identify features like sand boils, where sand and water erupt from the ground, and other deformations caused by liquefaction, providing further evidence of past events.
It's like the Earth is leaving its own fingerprints behind, telling us a story of its past.
A very apt analogy. And don't forget about tsunami deposits. In coastal areas, tsunamis can leave behind layers of marine sediment as they surge inland. By studying those deposits, scientists can learn about the history of past tsunamis.
So we're not just looking at what happened deep below the sea floor, but also understanding the traces left behind on land.
Absolutely. All those pieces of the puzzle contribute to a more complete understanding of past seismic activity, including the timing, the frequency, and the strength of those earthquakes. That knowledge is essential for assessing the risks we face and developing effective strategies to protect ourselves.
It's like having a blueprint of the Earth's seismic history, and it's all thanks to the meticulous work of these scientists.
Precisely. And speaking of meticulous work, let's shift our focus to what happens in the lab once those core samples are brought up from the depths. Remember, getting them to the surface is just the first step.
Right, that's where the real detective work begins.
Exactly. Scientists treat those core samples like precious artifacts, analyzing them with a whole range of techniques to extract as much information as possible.
It's almost like a forensic investigation, but instead of a crime scene, they're investigating the Earth itself.
That's a great way to think about it. It all starts with carefully describing and photographing the samples. Scientists note their color texture, the minerals they contain, any visible structures or features.
They're looking for anything that might tell a story, any clue that reveals something about the Earth's past.
Exactly. And it's not just a quick glance. They create detailed descriptions and photographs to document every nuance of the core's physical characteristics. Then comes sample preparation, where they carefully cut the core into smaller sections or slabs for further analysis.
So they're slicing up the Earth's history one piece at a time.
You could say that. And to really get a good look, they polish those cut surfaces to a high degree, revealing the internal structures and mineral grains in all their glory.
It's like polishing a gemstone to reveal its hidden beauty.
A beautiful analogy. This preparation allows them to do what's called petrographic analysis. They take very thin slices of the rock, mount them on glass slides, and examine them under a microscope. This allows them to identify the different minerals, the textures, and even figure out the rock's formation history. It's incredible the level of detail they can uncover.
It's amazing to think they can trace the history of a rock formation back millions of years.
It really is. But the investigation doesn't stop there. Next comes geochemical analysis, which is all about understanding the chemical makeup of the rock. They use techniques like X-ray fluorescence and mass spectrometry to figure out exactly what elements the rock is made of. Then they do isotopic analysis, which provides information about the rock's age, where it came from, and the conditions under which it formed. It's like unlocking a secret code hidden within the rock itself.
So they're piecing together a chemical history of the rock formation.
Exactly. And if there are fossils in the core, paleontologists get involved. They identify the fossilized organisms and study their evolutionary history, which helps to reconstruct the ancient environment in which the rocks formed. It's like bringing the past back to life.
It's incredible how all these different scientific disciplines come together to tell the story of our planet.
Absolutely. And we're not done yet.
Yeah.
Geophysical analysis adds another layer of information. They measure the rock's magnetic susceptibility, which tells them about its mineral composition and magnetic history. They also measure its density to determine its porosity and composition.
It's like they're giving the rock a full medical checkup.
That's a great way to put it. And finally, all this data is compiled and analyzed to understand the geological history of the region, how the rocks formed, and what the environment was like at the time. They then compare this data with other geological data, like seismic surveys and regional maps, to create a complete picture.
It's like putting together a giant jigsaw puzzle of the Earth's history.
Exactly. And this is where things get really exciting. Scientists use computer software to create 3D models of the subsurface, incorporating all that data from the core samples and other sources. These models help them visualize the geological processes that have shaped the region.
So they're not just looking at the past. They're using that knowledge to understand the present and even predict the future.
Absolutely. These 3D models can show them fault zones and areas that are prone to earthquakes and tsunamis. This is essential for assessing the risks and preparing for potential disasters.
It's like having a crystal ball, but one based on science and data, not magic.
A very apt analogy.
Wow.
And the findings from these studies often lead to new research questions and further investigations. The success of one drilling project can even inspire future expeditions to explore other interesting areas.
It's a never-ending quest for knowledge.
That's the beauty of science. It's all about pushing the boundaries of our understanding, and deep-sea drilling is a powerful tool in that quest.
But let's not forget why this research is so important. It's not just about satisfying scientific curiosity. It's about understanding our planet and protecting the people who live on it.
You're absolutely right. Earthquakes are a powerful force of nature, and they can have devastating consequences. Identifying the factors that could trigger future earthquakes is crucial for improving our ability to predict, prepare for, and lessen the impact of these events.
So let's delve into that aspect in more detail. Why is identifying those triggers so crucial?
Well, first and foremost, it allows us to develop more accurate and timely early warning systems. Imagine being able to give people precious seconds or even minutes to take cover or evacuate before the ground starts shaking.
Those seconds could mean the difference between life and death.
You're absolutely right. Identifying potential triggers also helps us refine our probabilistic forecasts, which estimate the likelihood of an earthquake occurring in a particular area within a certain time frame. This information is essential for long-term planning.
So it's not just about those immediate warnings, but also about making informed decisions about infrastructure and how we design our communities.
Precisely. Knowing about potential triggers can inform how we design buildings, bridges, and other critical infrastructure, making them more resistant to seismic activity. We can literally build for the future with earthquakes in mind.
It's about being proactive and not just reacting after the fact.
Exactly. And don't forget about emergency response planning. Understanding the potential for earthquakes helps communities develop effective plans, including evacuation routes, shelters, and medical services. It's all about preparedness.
Right. It's about being ready to respond effectively when an earthquake does happen.
Absolutely. Identifying high-risk areas also allows individuals and businesses to assess their own risk and take out appropriate insurance. Governments can make informed decisions about land use and development in those vulnerable areas. It's all about proactive risk management.
So while we can't predict earthquakes with 100% certainty, identifying potential triggers gives us valuable tools to prepare for and mitigate their impact.
Exactly. And while earthquake prediction is a complex field and we still have much to learn, ongoing research is vital to advancing our understanding. Each discovery brings us closer to a future where we can live more safely alongside these powerful forces of nature.
It's a reminder that science is an ongoing journey, a constant process of learning and adapting.
Now let's take a moment to acknowledge the human and economic costs of earthquakes. They are among the most devastating natural disasters, causing immense suffering and disruption. Improved prediction and preparedness can play a crucial role in reducing those losses.
The human cost is immeasurable, from the loss of life and injuries to the psychological trauma that people experience long after the earthquake is over.
That's right. A major earthquake can result in thousands of deaths, especially in densely populated areas and regions with inadequate building codes. Countless more people are injured, often requiring extensive medical care. And the psychological impact can be profound, leaving survivors to deal with post-traumatic stress disorder, anxiety, and depression.
It's a stark reminder that earthquakes don't just affect buildings. They affect the lives and well-being of people.
Absolutely. And the economic costs are just as significant. Earthquakes can cause widespread damage to buildings, roads, bridges, and other essential infrastructure. This disrupts supply chains, halts production, and damages vital facilities, leading to major economic losses.
It's like a domino effect, impacting every aspect of society and the economy.
Exactly. Businesses and industries can be crippled, and the cost of rebuilding damaged infrastructure and homes can be astronomical, especially in developing countries. Insurance claims related to earthquake damage can put a huge strain on both insurance companies and governments.
It's a sobering reminder of the immense challenges that earthquakes pose.
However, there's hope. Advancements in earthquake science and technology offer a path toward a safer future.
How so?
Imagine a world where early warning systems give people enough time to take cover, where buildings are designed to withstand the forces of an earthquake, and where communities are well prepared with effective emergency response plans. These are not just dreams, but achievable goals with continued research and investment.
It's about turning vulnerability into resilience.
Precisely. Improved risk assessment can help insurance companies better manage their risks and offer more affordable coverage. Effective disaster response and recovery plans can minimize economic losses and help communities recover faster. It's about breaking the cycle of devastation and building a future where we can coexist with earthquakes more safely and sustainably.
That's a future worth striving for. Speaking of striving for knowledge, we can't forget about the amazing vessel that makes much of this research possible. Chikyu. It's a marvel of engineering purpose-built for deep-sea drilling.
Chikyu is truly a testament to human ingenuity. It's a floating laboratory that allows us to explore the Earth's crust and mantle by drilling deep beneath the ocean floor. It's like a window into our planet's history and a key to unlocking the secrets of those incredible geological processes.
It sounds like something straight out of a science fiction movie.
It's real, and it's pushing the boundaries of scientific exploration. Let's talk about how it actually works. One of its most important features is a dynamic positioning system. It's a marvel of technology that allows Chikyu to stay perfectly positioned over the drilling site, even in strong currents and rough seas. It's like a carefully choreographed dance between GPS acoustic positioning and thrusters, keeping the vessel steady amidst the ocean's constant movement.
It's amazing they can achieve that level of precision in such a dynamic environment.
It really highlights the skill and ingenuity of the engineers who designed and built this incredible vessel. But the real star of the show is the drilling rig, a complex system of pipes, pumps, and motors that does the heavy lifting of drilling into the seafloor.
It's like a giant robotic drill biting into the Earth's crust.
A very apt analogy. And the drill bits they use are no joke either. Some of them even tipped with diamonds to cut through those tough rock formations.
Diamonds. Wow, they're not messing around.
They're going for it. And another crucial component is the riser system. It's a long, flexible pipe that connects the drilling rig on the vessel to the seafloor. It acts like a barrier, preventing seawater from entering the borehole and allowing them to control the flow of drilling fluids.
So it's like a lifeline maintaining a controlled environment within the borehole.
Exactly. And those drilling fluids play a vital role too. They're pumped down the drill pipe to lubricate the drill bit, cool the equipment, and carry away the rock cuttings from the borehole. They also help stabilize the borehole walls to prevent collapse.
It's like a carefully orchestrated dance of fluids and machinery all working together to reach those depths.
Precisely. And as the drill bit penetrates the Earth's crust, it collects those valuable core samples of rock and sediment. These samples are brought to the surface and analyzed in labs, giving us glimpses into the Earth's history and composition.
Those core samples are like time capsules holding secrets from millions of years ago.
And Chikyu makes sure those capsules are retrieved safely and efficiently. But it's not just about brute force drilling. Real-time monitoring is crucial. They have a whole array of sensors and instruments that track the drilling progress, detect any anomalies, and allow for real-time adjustments. This data is constantly being transmitted to scientists on board the vessel and ashore, so they're always in the loop.
It's like having a live feed from the depths of the Earth.
A very accurate description. And the scientific goals they're pursuing with Chikyu are as diverse as the Earth itself. It's used for earthquake and tsunami research to study climate change, investigate underwater volcanoes, and even explore those fascinating microbes that live in the deep sea.
It's a versatile platform for scientific discovery.
Exactly. Chikyu is a symbol of humanity's quest to understand our planet from its fiery core to the depths of its oceans. It reminds us that we live on a dynamic, ever-changing world, and that science is our most powerful tool for unraveling its mysteries and ensuring our future.
It's been an incredible journey so far, and I can't wait to see what we uncover next. Okay, so we're back. We've gone deep into the Japan Trench, explored the world of deep sea drilling, and now we're going to blast off to other planets.
Yeah, it's amazing to think that what we're learning here on Earth about its deep history and the forces that shape it can help us understand those distant worlds out there in space.
It's like using our knowledge of Earth as a guidebook to explore the universe. But how does that actually work? I mean, Earth is pretty unique, right, with its, active plate tectonics and all.
It is, but the fundamental processes, the physics and the chemistry that govern those processes, they're universal. Gravity, pressure, heat, the interactions between elements, those things work the same way everywhere in the universe.
So it's like we're speaking the same scientific language even when we're looking at different planets.
Exactly. We can look at pictures of other planets and see mountains, valleys, volcanoes, even fault lines, and compare them to what we know about Earth. It's like looking for familiar patterns in an alien landscape.
And we're not just limited to what we can see with telescopes, right? I mean, we have data from spacecraft, all those measurements of gravity and magnetic fields, and the shape of the planet's surface.
That's right. That data can tell us so much about what's going on beneath the surface. It helps us figure out if a planet has a molten core, if its crust is moving, even if it's ever had volcanoes. And all that helps us piece together the story of how that planet evolved, how it got to be the way it is today.
So we're not just looking for signs of life. We're trying to understand the whole lifespan of a planet from its birth to its present state.
Exactly. And plate tectonics, even if it's not exactly like on Earth, can play a huge role in shaping a planet's destiny. It influences where continents form, how oceans are created, even how carbon dioxide cycles through the planet's system.
So by studying those processes on other planets, we can get clues about their climate history and whether they could have ever supported life.
That's a big part of it. And there's another aspect to consider: resource formation. Plate tectonics is like a giant mixer, churning up the planet's interior and concentrating valuable minerals and energy resources in certain areas.
This is like a treasure map showing us where the good stuff might be.
Yeah, kinda. But of course, the biggest question of all is, are we alone in the universe?
That's the one that keeps us all looking up at the stars.
And here's where things get interesting. Volcanic activity, which is often linked to plate tectonics, can release gases that contribute to a planet's atmosphere. And that atmosphere, its composition and thickness, is crucial for habitability.
Right, because here on Earth, our atmosphere is what makes life possible. But what about those deep sea vents we talked about earlier? The ones that are teeming with life even in the darkness of the ocean floor.
Those are amazing. And they're often found in areas with lots of tectonic activity where hot water and minerals are spewing out from the Earth's interior. Some scientists believe those vents could be a model for how life might arise on other planets, especially those with water beneath their surfaces.
So the same forces that shape our planet, those incredible tectonic processes, could be creating environments where life could exist on other worlds.
It's a possibility that scientists are really looking into. And while we haven't found definitive proof of plate tectonics on other planets, yet our understanding of Earth gives us a starting point, a set of clues to look for as we continue to explore.
It's like learning to read the language of planets, deciphering the stories they have to tell.
Exactly. And as our technology gets better, as we send more probes and telescopes out into space, we'll gather more detailed information, refine our theories, and maybe even make some groundbreaking discoveries.
Wow, this has been an amazing deep dive. From the depths of the ocean to the far reaches of space, we've explored some seriously cutting-edge science, uncovered the interconnectedness of our planet, and pondered the mysteries of the cosmos. What a journey.
It really highlights the power of scientific inquiry, the human drive to understand the world around us, both near and far.
It's been a blast. And to all you listeners out there, keep exploring, keep asking questions, and keep diving deep into the mysteries that surround us. You never know what you might discover.